need to learn a couple more things that expand upon what we've already been talking about. So here we have a block that's hanging on a string and we have it at A and let it go at A and it swings through B and C and D and back up to E. Where is the tension going to be the least? At A and E, what's the tension going to be there? Zero, because the weight is pulling straight this way and there's nothing pulling that way. That makes sense? So at A and E, it would be slack. It would not have tension in it. So that's going to be least. Where is it going to have the most tension? C. Why is it going to have the most tension at C?
Gravity's pulling it down.
The weight is definitely pulling the most direct here. Here the weight is pulling down, but it's pulling both down and over, and so the down part is smaller. But here we're going to get the most of it there, but there's something else going on also. It's not just weight. As it's swinging through that arc, we have
Kinetic energy thing.
well, we do have kinetic energy thing, but we have centripetal force. So
I'm stupid.
we're pulling in on all these. We're not really pulling in up here and here because we stopped moving at those points. And so where is our movement going to be the fastest? At C, and so that's where the centripetal force is going to be the greatest because that's where we have the greatest velocity. So for those of you who forget, Fc is equal to mv squared over r.
Yes.
And so at this point, again, what forces are pulling to make the tension here? The weight and the centripetal force. They're both pulling, so we need centripetal force. We also need weight. How do we know how fast it's going when it gets to C? Up here we have potential energy, and it's going to fall a certain distance, and all that potential is going to turn into kinetic energy at that point. So, understanding those concepts, I want you to figure out a formula that would solve for tension right here. So, I'll give you about 5 minutes on that one.
What's R?
As it was now. So, we know that the tension was equal to the weight and the centripetal force, right?
Yes.
We know the weight is mg, and we know the centripetal force is mv squared over r. Now, where did the v come from? The v comes from the fact that we lost potential energy, which means we gained kinetic energy. So we say the mgh lost equals the mv squared over 2 gained. And then we say, hey, look, those m's go away. And then I bring the 2 up and I have 2gh equals v squared. So I say, hey, this v squared can replace that v squared. So I have mg plus m, and instead of v squared I have 2gh, and again over r. And then as many of you astutely noticed, if the radius is here, hey, the radius is the height it drops. So you say, hey, this height is really radius, which means that cancels out. And then if we make that look more nicer, we get mg plus 2mg, which equals
3mg.
3mg. Or as most would like to say, that was 3w. Which works also because, yeah. So either one of those works. That makes sense? So the tension at that lowest point is just going to be 3 mg. Well, what would it be over here at B? Did we fall as far? Yeah, from A all the way down to C, we lost all of the radius, right? But for B here, we only lost this much of the radius. So if we know this angle, then we're looking at the which side? Yeah, we're looking at the adjacent side, so it's cosine. So at B or at D, the tension is going to be 3 mg cosine. So that's all I have to do for that. So once you figured out the algebra, that wasn't too bad. Then you say, well, it gets really easy from there. So you can figure out the tension at any point very easily from knowing the angle. It's kind of fun doing that algebra, right?
It is.
You feel so smart when you're done with the whole thing. Okay, so our last one is we dealt with things going at an angle and hanging straight down, but what if two things are two things are on two different angles? First, we'll start this off with no friction, so it's nice and easy. So we're going to call this 68 degrees over here, and this 32 degrees over here, and I'm going to call this 2.9 kilograms. I'm going to call this one 1.5 kilograms. And we want to know what is the tension in the string once this is moving. So again, we're going to start off with no friction, and we'll let you figure this part out. Okay, so in here, before we can find our tension, of course, that's going to be m times g plus or minus a, right? And so before we can get this, we got to find our a, and of course we know that a is equal to f net over m. Which m am I talking about accelerating? Both of them combined, so we're going to have the 2.9 plus the 1.5 is going to be the mass. The F net here, we have to say, well, what forces are fighting? Well, the forces that are directly fighting are the F parallel going this way and the F parallel of the weight going this way. So we're going to have the mg sine theta over here. So 2.9 times g times the sine of 68 minus the 1.5 times g times the sine of 32. So if we subtract those out, that's going to give me my F net. Right?
Yes.
Always.
Yeah. So then that F net divided by the m should give me, what did we get? 4.2. 4.2?
Yeah.
So we got 4.2 meters per second squared after doing that whole thing. Then when we plug into the T tension formula, the mass on the left side is going to be 2.9, and the G is going to be 9.81 sine 68 minus, why am I minusing? Because yeah, this one's going to go down and this one's going to go up.
Okay, so the heavier one?
So whenever we go down, we subtract. So we're going to subtract the 4.2. And if we do that whole mess, we get 14 newtons. And if we try that over on this side to see if we get the same number, which is a nice check, we're going to have 1.5 times g sine theta. And this time we're going to add the 4.2. And if we do that, we again get 14 newtons over on this side. Now, another way to slightly look at it, which might be easier for some of you this might just confuse you, I'm not sure which, but we end up using g sine theta both here and here. It's something that pops up a lot, so you can just kind of think of this as m times the new g. And so if you want to, you can just say, well, what is g sine theta over on this triangle? So if we just take g sine theta over here and use it, that would turn out to be 9.1 meters per second squared. And if we did the same thing over here, that turns out to be 5.2 meters per second squared. And then you can just kind of plug straight into this equation. Instead of writing g, you just use this number as your g on the left side and this number as your g on the right side.
Oh, okay.
And you could have used that in this situation too. So we could have just had like 2.9 times 9.1 minus 1.5 times 5.2 as our net. Does this make sense?
Yeah.
So if you do this ahead of time, it does make things a little bit faster to plug in, if that made any sense at all.
Yeah.
Okay, so for some people that's more helpful. Yeah, it makes it a little less tedious to plug into the calculator, basically. So if that's easier to wrap your head around, then groovy. Last thing we'd like to do, of course, is to
Add friction.
add friction. So
Also,
do we want to use similar numbers, or we want to throw in completely new numbers? Completely new numbers. Yeah, like that too.
Make them unrealistic, like 273.
Please. Okay, so this is going to be 4.6 kilograms over here. This angle looks like 76 degrees, and we're going to have a mu on this side of 0.397. Over here, this is a 30-degree angle. The mu is going to be 0.417, and this log is 2.9 kilograms. So now that we've introduced friction into the equation, of course, that's going to change the F net part of the equation. So try and figure out F net. First thing we need to do, of course, is find A is equal to F net over M. Now the M is really easy. That's going to be the combined masses again. So we're going to have 4.6 added to the 2.9 down on the bottom. That part's easy. But then we say, well, what is my F net at the top? Well, the parallel portion of this one is trying to make me go faster that way. The parallel portion of this one's trying to make me go faster this way. And who's going to win?
4.6.
Yeah, you would hope that 4.6 at a steeper angle is going to be 2.9 at a shallower angle, right? So the motion's going to be to the left. So if the motion is to the left, then friction wants to pull this way, and friction wants to pull this way, because this one's going to end up going up the hill, this one's going to end up going down the hill, friction's going to oppose both of that. So you look at this and you say, well, this one is trying to fight all three of the other ones. So all we have to do is figure out what each of those is. So I did it in chunks like this just because I think it's easier to show you. But if you found the F parallel here, I got 43.79. And when I did the FF here, I got 4.33. Those are all in Newton's before. And when I found the F parallel on the other side, I found 14.22. And the friction on this side was 10.27. Those numbers look realistic for you guys?
Yeah.
So again, for those of you watching at home, F parallel was mg sine theta, and the F we used was mu mg cosine theta. And so if you just plug all those in, you got it made to get those numbers. So clearly the F net here is going to be the 43.79 minus the 4.33 minus the 10.27 minus the 14.22. Because all those three were fighting that one. So then the F net divided by the M, that should have come out, mine came out to, yours should have been similar. So then we get into the fun tension part. Well, how do we find the tension here? Well, again, I'm going to go with what is G on either side. So if we just do the G sine theta over on this side, G on this side turns out to be 9.52. And the G over here, since we're at the sine of 30, that's going to be half. So we're going to have 4.905 is going to be G on that triangle. So the tension again is going to be M, G plus or minus A. So the M on this side, we're going to use the 4.6 kilograms. And we're going to use the G of 9.52. That's just G sine theta. And then again, since this one's going down, we're going to subtract the A of 1.996. And then there's one more step that we'll talk about in just a second. And the T over on this side, it's going to be 2.9 times its G. That's G sine theta. And then this time, of course, we're going to add because it's going to go up. And then there's going to be something else. So some of you got to this part and you said, well, hey, this turned out to just be 34.6, and this one turned out to be 20, and you panicked and you said, they're not the same, they're not the same. You're right, because we didn't include the friction. Now, this friction happens before we get to the rope. So this one, again, since we're subtracting, what we're going to do is we're going to subtract its friction. So if we subtract its friction on this side, what was our friction on this side? 4.33. So we're going to subtract 4.33. Over here, the friction is pulling against the rope's motion, and so it's going to add to it. So if we subtract this friction on this side and we add the friction on this side, I ended up getting 30.3 is over here and 30.3 is over there. And they're the same! Yay! Hooray! Can't we just be done? So now you should have enough information to be able to finish problem D, which doesn't get any worse than that. And most of them are a lot easier.